AM, amplitude modulation. Amplitude modulation, AM, is one of the oldest and simplest ways to send information via radio waves. It works by varying the amplitude, strength, of a high-frequency carrier wave in direct proportion to the instantaneous signal of the data you want to send, like your voice. Think of it like a flashlight. If you quickly make the beam brighter and dimmer to signal a message, you are performing a simple version of amplitude modulation. The core components to create an AM signal: you need three basic elements: message signal, the actual information, audio, music, or data. It is typically a low-frequency signal. Carrier wave, a high-frequency sine wave that carries the message through the air. It has a constant frequency and amplitude before modulation. Modulated signal, the final output where the envelope, the outer boundary, of the carrier wave matches the shape of your message signal. How it works mathematically: in simple terms, the transmitter multiplies the message and the carrier. The standard equation for an AM wave is: where is the carrier amplitude? Is the carrier frequency? Is the message signal? As increases, the peaks of the radio wave get taller; as decreases, they get shorter. The modulation index, this is a critical value that describes how much the carrier is being stretched or squeezed by the message. Under modulation, the message is clearly preserved. This is the ideal state for clear audio. 100% modulation, the carrier amplitude hits zero at its lowest point. This uses power most efficiently without losing data. Overmodulation, the signal becomes clipped or distorted because the carrier cannot have negative amplitude. This causes the audio to sound buzzy or broken at the receiver. Pros and cons of AM feature description: AM signals, especially in the medium wave band, can travel advantage, range hundreds of miles by bouncing off the Earth's ionosphere. Advantage: receivers, radios, are incredibly cheap and easy to build. You only simplicity need a diode and a capacitor to detect the signal. Lightning, power lines, and engines create electrical sparks that disadvantage, noise change signal amplitude. AM radios interpret this as static. Disadvantage: most of the power is wasted in the carrier wave itself, which contains efficiency, no actual information. Where is AM used today? While FM, frequency modulation, replaced AM for high-fidelity music, AM is still vital for commercial AM radio, news and talk shows that need long-distance coverage. Aviation, pilots and air traffic control still use AM because it handles signal fading better than FM for critical voice instructions. QAM, Quadrature AM, a modern digital version used in Wi-Fi and 5G to pack massive amounts of data into a single signal. Phase modulation, PM. Phase modulation, PM, is a form of angle modulation where the phase of a high-frequency carrier wave is varied in direct proportion to the instantaneous amplitude of the message signal, such as audio or digital data. While it is rarely used for analog radio broadcasting, unlike AM or FM, it is the fundamental building block for almost all modern digital communications, including Wi-Fi, 4G/5G, and satellite TV. How it works: in phase modulation, the carrier's amplitude and frequency remain constant. Instead, the timing or the starting point of each cycle of the wave is shifted. Positive voltage: if the message signal's voltage goes up, the phase of the carrier wave shifts forward, advances. Negative voltage: if the message signal's voltage goes down, the phase of the carrier wave shifts backward, delays. The mathematical equation: the mathematical representation of a phase-modulated wave is, where, constant amplitude of the carrier, constant frequency of the carrier. The message signal, data. Phase sensitivity, which determines how many radians the phase shifts per volt of the message signal. PM versus FM, the close cousins. Phase modulation and frequency modulation, FM, are both types of angle modulation. 8 They look very similar on an oscilloscope because a change in phase naturally causes a momentary change in frequency. Frequency modulation feature: phase modulation, PM, FM, controlled parameter phase, frequency, proportional to amplitude of the message. Amplitude of the message instantaneous proportional to the derivative, slope, directly proportional to the frequency of the message. Message. Common use: digital data, Wi-Fi, satellite, analog audio, FM radio. Pro tip: you can actually create an FM signal using a phase modulator by first passing the message through an integrator circuit. Digital evolution, phase shift keying, PSK. In the digital world, PM becomes phase shift keying, PSK. Instead of a smooth analog curve, the phase jumps between discrete values to represent bits. BPSK, binary PSK uses two phases, and, to represent 0 and 1. QPSK, quadrature PSK uses four phases, to represent 2 bits at a time, 0, 0, 0, 1, 10, 11, doubling the data speed. Why use phase modulation? High noise immunity: like FM, PM is very resistant to electrical static because noise usually affects amplitude, which PM receivers ignore. Efficiency: it is highly bandwidth efficient in digital systems. Power stable, because the amplitude is constant, the transmitter can operate at maximum power efficiency without distortion. Modulation index of PM in phase modulation, PM, the modulation index, often denoted as OR, is a dimensionless value that represents the maximum shift or swing in the phase of the carrier wave. While it performs a similar role to the modulation index in AM or FM, it has a unique definition and behavior that is critical for digital communications. 1. The formula for a single-tone message signal, like a simple sine wave, the modulation index is defined as, where, the modulation index, measured in radians. The phase sensitivity of the modulator, radians per volt. The peak amplitude of the message signal, volts. In PM, the modulation index is numerically equal to the peak phase deviation. 2. Key characteristic, frequency independence. This is the most important way PM differs from FM. In FM, the modulation index is inversely proportional to the message frequency. 10. If you double the frequency of your voice, the modulation index drops by half. In PM, the modulation index is independent of the message frequency. It only cares about the amplitude, volume, of the signal. Whether you whisper at a high pitch or a low pitch, if the volume is the same, the modulation index remains the same. 3. Bandwidth and sidebands. The modulation index determines how much space the signal takes up in the air. Narrowband PM, the signal is very thin and looks similar to an AM signal spectrum, with only 2 major sidebands. Wideband PM, the signal produces many sidebands. The number of active sidebands is determined by Bessel functions. As increases, more power moves from the center carrier frequency into the sidebands. 4. Why it matters in digital, PSK. In digital systems like BPSK, binary phase shift keying, the modulation index is usually fixed to a specific value to represent data. For BPSK, the phase shifts by radians. Here, the modulation index is essentially about 1.57 relative to the center, creating the maximum possible distance between a 0 and a 1 to prevent errors. Summary table, comparison feature. PM modulation index, beta, FM modulation index, beta, depends on amplitude. Yes, depends on frequency. No, yes, inversely, physical unit radians dimensionless ratio effect of doubling no change in is halved. Spectrum of phase modulation. The spectrum of a phase modulation, PM, signal reveals how the signal's energy is distributed across different frequencies. Because PM is a type of angle modulation, its spectrum is much more complex than simple amplitude modulation, AM. Instead of just 2 sidebands, it consists of a carrier and an theoretically infinite number of sidebands. Here is the breakdown of what the PM spectrum looks like and how it behaves. The structure, carrier and sidebands. When a carrier is modulated by a single tone message, a sine wave, the resulting spectrum contains a center carrier at the original frequency, sideband pairs located at, and so on. The amplitude of the carrier and each pair of sidebands is determined by Bessel functions of the first kind. The order of the Bessel function corresponds to the sideband number. The role of the modulation index. The modulation index $beta acts as the volume knob for the spectrum. If is small, narrowband PM, only the first pair of sidebands has significant energy. The spectrum looks very similar to AM. If is large, wideband PM energy spreads out from the center. Higher order sidebands become stronger, and surprisingly, the carrier power can actually drop to 0 at specific values of, called carrier nulls. Bandwidth, how wide is the signal? Even though the sidebands technically go on forever, most of the power is concentrated near the carrier. Engineers use Carson's rule to estimate the significant bandwidth required, the PM difference. In FM, if you increase the message frequency, the modulation index decreases, keeping the bandwidth relatively stable. In PM, the modulation index is constant regardless of frequency. Therefore, the bandwidth of a PM signal is directly proportional to the message frequency. If you double the frequency of your data, the spectrum physically takes up twice as much space. Power distribution. A key feature of the PM spectrum is that the total power remains constant. In AM, adding a message increases the total power of the signal. In PM, adding a message simply redistributes the existing power from the carrier into the sidebands. The total area under the spectral curve always stays the same. Summary comparison feature. AM spectrum, PM spectrum. Number of sidebands exactly 2 infinite, theoretically, sideband spacing, sideband amplitude linear, nonlinear, Bessel, total power increases with modulation constant. Carson's rule. The approximate bandwidth of a phase modulation, PM, signal is typically calculated using Carson's rule, which provides a practical estimation of the frequency range required to transmit about 98% of the signal's power. The general formula, Carson's rule, for a PM signal modulated by a single tone message, like a sine wave, the approximate bandwidth, is, where, the modulation index, peak phase deviation in radians. The frequency of the modulating message signal. Why PM bandwidth is frequency dependent? There is a fundamental difference in how PM and FM handle bandwidth. In a PM system, the modulation index $beta$ is constant regardless of how high or low the message frequency is. Because of this, the bandwidth of a PM signal is directly proportional to the message frequency. If you double the frequency of your audio/data, the bandwidth effectively doubles. In contrast, in FM, decreases as increases, which helps stabilize the bandwidth. Narrowband versus wideband PM. Depending on the size of the modulation index, PM signals are categorized into two types. Approximate type condition description bandwidth occupies very little space, looks similar to narrowband and AM spectrum with only two main PM sidebands. Spreads power into many sidebands, used wideband PM for high-fidelity data transmission. Practical example: imagine you are using a PM system with a modulation index of and you are sending an audio signal with a maximum frequency of. In this scenario, the signal would occupy approximately of the radio spectrum. Key takeaway for 5G/6G in modern digital systems, like 4G, 5G, or satellite, we use phase shift keying, PSK. In these cases, the bandwidth is primarily determined by the symbol rate, how fast we switch phases, rather than just the frequency of a single tone.